Hello everyone, welcome to the 11th tutorial class on digital communication. And in this class, we'll start a new module, that is digital modulation. And before going to the detailed discussion on the digital modulation techniques, we'll discuss geometric representation of signal, which is very informative tools to analyze the noise immunity of a particular digital modulation technique. And after that, we'll discuss different type of digital modulation technique, and from them we'll only discuss about amplitude shift keying and its generation and detection techniques for this presentation only. Now, okay, now move to the next slide. So modulation, as you already know, that modulation is very crucial steps for communication, and it is required for long distance propagation of signal and reduction in the antenna size. And there are also other reasons, but these are most important reason to use the modulation techniques, where some characteristic of a carrier signal, which is high frequency signal, is varied according with the modulating signal or low frequency signal or baseband signal. Okay. And in case of digital modulation technique, the difference is only that we'll use a binary sequence or digital signal as baseband signal, and use a cosine or sinusoidal signal, which is high frequency, for the modulation purpose. Okay. So in case of analog modulation, the baseband signal is analog in nature, whereas in case of digital modulation, the baseband signal is binary sequence like 1010, etc., etc. Okay. Now, digital modulation techniques are mainly classified into basic three types. One is amplitude shift key, formally it is known as the ASK. Next one is the frequency shift keying, which is also known as the FSK, and last one is the PSK, which is also known as the phase shift keying. Okay. So in case of ASK, the characteristic or the amplitude of the carrier is varied according with the digital or binary sequences. Next, now, whereas in case of FSK, frequency of the carrier is varied according with the digital signal, and in case of PSK, phase of the carrier signal is varied according to the corresponding digital signal. Okay. Now, before going to the detailed discussion about these different techniques for the generation and detection like ASK, FSK, and PSK, let's discuss about the geometric representation of signal, where we represent signals in terms of energy signal geometrically, which is very important tools as it provides a mathematical basis for the analysis of noise immunity in very satisfied manner. Okay. So from the corresponding geometrical representation of a signal, if we draw that or if we plot that, we can easily understand the noise immunity about the corresponding digital modulation technique. So what do we do actually in geometric representation of signal? Uh, Basically, it's a very large topic. In this case, in this tutorial class, we will just get the brief idea about the geometric representation of signal, which is just the thing which is required to understand the uh, corresponding digital modulation technique. Okay. So in case of geometric representation of signal, we represent any set of m energy signal which is represented by SIT as a linear combination of n orthonormal basis function phi it. Okay. and where n less than equal to m. Okay. This means for a given set of real valued signal like S1t, S2t, SMT, and which have duration of t second, then we can write that original signal SIT is summation of from j equal to 1 to n phi j multiplied by Sij, where that means Sij are different number of symbols. Okay, so where t the range of the t from remain from 0 to t, and I will be from 1 to m. Okay, so what is phi j? Phi j is the real valued basis function, and it has the following property. From integration of phi I t and phi j t will be 1 if I equal to j, and else it will be 0. Okay, so now SIT can be plotted with respect to phi j orthonormal plane. Okay, and which is formally known as the signal space diagram. So all these are basically look like some kind of mathematical equation. It will be very easy to understand if we uh, draw geometric representation of signal. For some example, we'll understand the whole idea in case of ASK, which will be discussed in the upcoming slides. Okay, so just get the idea about that. Geometric representation of signals is nothing but we want to represent any signal with respect to its energy signals, and also as its linear combination of n orthonormal basis function phi I t. Okay. Okay, so coming to the first digital modulation technique, which is amplitude shift keying ASK. As we already told that in case of ASK modulation technique, amplitude of the carrier is varied according with the baseband signal. Okay, that is uh, as it is the digital modulation, that means we only consider 1 or 0 for the binary 1 or 0 in for binary sequence or digital data. So for ASK, only carrier will be present depending on the 1 or 0. Okay, so there is only one unit energy carrier, and it is depend on the input binary sequence. Hence it is also known as on off key modulation. Okay, so you can see that this one is the corresponding arbitrary digital data or binary sequence like 1 or 0, and basically this is unipolar representation. Here you can see that 1 is represented by some, you can say that this one is the plus 5 volt and 0 is represented by 0 volt. 1 is plus 5, 0 is 0 volt, like this, and this one is the carrier signal. So how can you get the ASK? So if you want to get the ASK, just we need to multiply this binary input sequence signal with the carrier signal. So where the input voltage is high or plus 5 volt, there it is multiplied and you get the corresponding voltage level, and the output will be look like this. But where the uh, input voltage level input binary sequence is 0, where the voltage level represent which is represented by the 0 volt. So if you multiply them 0 with the corresponding carrier signal for this region, for this time span, it will be 0. Okay, so you can see that the amplitude of the carrier is varied according to the binary input sequence. So for 1 we get the corresponding carrier signal, and for 0 we don't get any kind of signal. Okay, so it is that's why it is also known as the on off key. So in case of 1, we get the corresponding ASK output, that means it is on, and for 0 we don't get any kind of carrier, that means it's off. Okay, so this is called as also on off key modulation. And how can we get ASK signal? So ASK signal is basically product of binary sequence and the carrier signal, that's all. So this is the waveform for ASK signal. Now coming to the mathematical analysis of ASK. So if we represent ST1, that means energy signal, sorry, signal for the 1 that will be nothing but 1 multiplied by a cos 2 pi fct. Let's consider the corresponding carrier is a cos 2 pi fct, where a is the maximum amplitude of the carrier and fc is the frequency of the carrier. And so for the one corresponding corresponding equation will be 1 into a cos 2 pi fct. So that will be a cos 2 pi fct. And for the symbol 0, the corresponding waveform or output is 0 multiplied by a cos 2 pi fct, that is 0. So you can, as we already seen from the earlier slide, that for this region there is no waveform. Okay, so for this region the expression is 0, and for this portion a cos 2 pi fct. Okay, so that's why you write this st1 for 1 and st for 0. Now this is the formal expression. Now if you want to draw the geometric representation of ASK, so we need to substitute them, or we need to use the energy signal. We need to use the energy signal. So basically, mm, uh, uh, mm, you can see that we know that for a sinusoidal signal, PS equal to a square by 2. Okay, that means power equal to its maximum amplitude square by 2. So a will be root over 2 ps. So now if you substitute the amplitude a with root over 2 ps, root over 2 ps, so it will look like this: st1 equal to root 2 ps cos 2 pi fct. Okay, so now this equation is in form of power, but we want to get in term of energy. So we know the relationship between energy and power is eb equal to ps into tb. So if you if you want to get that, so just we divide the whole equation by tb, and again multiplied it by tb, so root over ps by tb into root 2 by tb. So we just rewrite the equation like this. So as EV equal to PSTB, so ST1, so the modified equation will look like this: ST for 1 equal to root over EB into root 2 by TB cos 2 by FCT. Okay, yeah. So as EV equal to 2, so we can write like this: EV equal to PSTB. So we write the energy, the symbol, sorry, for the symbol 1, st will be root over eb into phi 1t, and st0 equal for st for symbol 0 will be 0 into phi 1t. So phi 1t is the real valued function, real valued basis function or orthonormal function. Here we only use one kind of orthonormal function or real valued function, and which is nothing but root over 2 by tb cos 2 by fct. Okay, so in case of ASK, the number of orthonormal function is only one, and which is nothing but root over 2 by tb into cos 2 by fct. Okay, so so orthonormal function is nothing but carrier function. Okay, so by using above two equation, we can plot signal space diagram for ASK. So what is the signal space diagram? That is not in case of signal space diagram, we just plot the corresponding value of energy with respect to the orthonormal basis function. Okay, so here the orthonormal basis function, real valued function or orthonormal function is phi 1t. So if we uh, if we plot the different energy for different symbol with respect to phi 1t, then the corresponding plot will be nothing but signal space diagram. So here you can see that if we consider an axis phi 1t, and we plot the corresponding energy for 1 and symbol 0 on that axis, so corresponding output will be nothing but signal space diagram for the ASK. So here you can see that this one is the corresponding axis in phi 1 2. So for a symbol 0, the corresponding energy is 0. So for 0, we represent symbol 0 at this point, which is nothing but 0. But in case of 1, we know that this one is nothing, the corresponding energy is root over eb, okay, or root over pstb. So for the symbol 1, the corresponding it will be represented by this point. Okay, so this one is the symbol 0, this one is the symbol 1, and its the value at this point or energy is root over ps into tb. Okay. Now the distance between two symbols like symbol 0 and symbol 1, that is nothing but root over ps minus tb minus 0. Okay. And this distance denote the corresponding noise immunity. The more the distance, the more noise immunity for particular digital modulation technique. So it is always expected that the distance between these 2 points will be maximum. Okay. So the additional d will be root over ps into tb. So that is nothing but the signal space diagram for ASK. Okay. And we can see that how can we ex, uh, express or geometrically express signal geometrically. You can see that st1 and st0 are expressed in term of phi 1t or carrier signal. Okay. So this representation is the geometric representation, and this plot is signal space diagram where we plot energy of the corresponding signal with respect to real valued basis function or the orthonormal function or the carrier signal. Okay. This is as simple as that. Now coming to the next slide. Now we want to draw the power spectral density of ASK. So power spectral density of ASK, it is similar to the amplitude modulation for analog modulation technique. So we already know that for normal aim, if we want to observe the spectrum, the corresponding spectrum for modulated wave, the spectrum has been shifted to the plus minus fc. Here similar thing happens in case of ASK. The corresponding spectrum has been shifted to the plus minus fc. You can see that this spectrum is the only this spectrum is the for uh, pulse for the rectangular function, okay, or baseband signal, this spectrum. And as we use the ASK, that means as it is multiplied by the cosine or sinusoidal signal, so the overall spectrum will be shifted to the corresponding frequency of the carrier signal, that means plus minus fc. Okay. And the theoretical bandwidth of the ASK will be infinite. Here you can see that, but uh, practically 95% power of the spectrum is centered at plus minus fc, and we can it can be seen that uh, corresponding bandwidth is 2 by tb, okay, or 2 fb. You can see that this point is fc minus 1 by tb, and this one is the fc plus 1 by tb. So in between them, maximum or 95% power will remain. Okay. So this will be the uh, practical bandwidth for the ASK, that is 2 fb. Clear? So this is the power spectral density of ASK. Now coming to the generation of ASK, how can we generate ASK? So it is already told that if we use ASK is just product of uh, input binary sequence and its carrier. So if we use a product modulator whose one input is unipolar input data or binary sequence or digital data, and another input is the carrier, which is nothing but root 2 ps cos 2 pi fct. So output of the corresponding product modulator is ASK. So if we multiplied a binary sequence with a cosine signal or sinusoidal signal, that we get corresponding ASK or amplitude shift key modulated wave. Okay. Next, detection of ASK. So after the ASK modulation, it is of quite advised that how can we demodulate the ASK modulated wave. How can we extract the original baseband or message signal from the ASK modulated wave? Well, there is there are two approaches. First one is the coherent detection or synchronous detection, and last one is the non-coherent or non-synchronous detection. So first one is the coherent detection. It is again uh, similar to the AM. Okay. So in case of coherent or synchronous detection, the corresponding block diagram is shown here. You can see that it consists of a product modulator an integrator, and a decision device. Okay, so these the three parts of the uh, coherent detection for the demodulation of ASK. Okay, and in case of coherent or synchronous detection, we use a locally generated carrier whose frequency is the same as the corresponding uh, modulating carrier frequency. Okay, exactly same, and the value of the this frequency is known to us. Okay, so obviously we can say that total process is synchronous. That's why we called as the coherent or synchronous detection technique. So here we use a we use a locally generated sinusoidal signal for the demodulation purpose whose frequency is known to us. Okay, now let's see how it work. So you can see that for first part is the product modulator. So one input is ASK input ASK signal, and another input is carrier wave 2 pi fc. So if we multiply them, we can get here you can see that st1 is the incoming signal, root over 2 ps cos 2 pi fc. Now output of the product modulator is st1 multiplied by another cos 2 pi fct. So root 2 ps cos 2 pi fct into cos 2 pi fct. Okay, so that is another root over 2 ps cos square 2 pi fct. So if we express it like this, root 2 ps 1 plus cos 4 pi fct. Okay, now this output, the output of the product modulator is going to the integrator part. Okay, so what is the function of integrator? The first integrator function is similar to the low pass filter action. Okay, so here you can see that it is essentially perform low pass filter action on the output of the multiplier on successive bit interval. So what will happen? So if we use this signal as the input of the integrator, the corresponding output will be root 2 ps integration 1 into dt and integration cos 4 by p dt with interval from 0 to tb. Okay, so if we use the interval 0 to tb, so obviously we get the this will be become 0 part 0, and we get this value 2 into ps in multiplied by tb duration. Okay, so this is nothing but a dc voltage level, okay, which is particular value. Now output of the integrator is going to the decision making device. So what is the decision making device? So here we use a threshold value. So if the output of the integrator is greater than the threshold level, so obviously corresponding output will be 1, and if the output of the integrator is less than the corresponding threshold, the corresponding output will be 0. So that is the decision making device. That means ultimately we need to identify either the baseband signal is 1 or 0. So based on this decision making device, we can get 1 or 0. Okay, so this is the basic operation of coherent detection. Okay, now coming to the next type of detection, non-coherent detection, so or asynchronous detection. So in case of non-coherent or asynchronous detection, we don't use any kind of locally generated carrier frequency or locally generated sinusoidal signal. Okay, instead we use a rectifier, a low pass filter, a comparator or decision making device. Okay, so let's see how it work. So you can see that the at the initially we receive the modulated ASK signal in the rectifier end. Okay, so if we use rectifier, the corresponding output of the rectifier will be look like this. That means the negative part of the signal will be off. Okay, so we get the positive half of the output, and it will you can see that it will look like this, and the negative half will be suppressed. Okay, now coming to the obviously this is the half wave rectifier. Now the output of the rectifier is applied to the low pass filter. Well, you can see that the for this signal it consists of two type of signal. First one is the, you can see that the hidden carrier signal and the corresponding envelope where the low pass frequency or the baseband signal is hidden. Okay, so basically the output of the rectifier has two part. One is high frequency component, that is carrier, and this low frequency component, that is the message signal or digital or binary sequence. Okay, so the low pass filter originally what will do, it will do that it will pass the low frequency part. That means it will ultimately detect the corresponding envelope of the signal. Okay, so the low pass filter suppress the high frequency component and gives an envelope detected output. Okay, so it will look like this. So this is the basically the envelope. So this is nothing but the original data. Okay, now this voltage, this signal is going to a comparator where it will compared with a particular threshold level, and if the voltage level is greater than some kind of that threshold, it will be become 1 or it will be considered as the 0, and we get the ultimately digital output. Okay, so this is the non-coherent detection for ASK signal. I think there is no problem. So coming to the conclusion part, so we have studied basically what is digital modulation and the corresponding geometric representation of signal space diagram for particular digital modulation technique, and we also know the ASK generation and different ASK detection techniques. Okay, and we'll discuss FSK and PSK in the next classes. So these are the few references, and thank you. If you have any question, please post them.